Hello. Okay, very good afternoon. And let's come back to the batteries question and finish our chapter 5 today. So you have seen today is very busy congregation graduations. Hopefully that will be you some years from now. Okay. uh, okay, so just to have a little refresher of your memory, that what we did last time was to talk about batteries. And battery works because we have a redox reaction and the electrons is being lost by one of the substance and then gained by another substance. And a battery works when we separate this redox into two parts, when we have one side doing reduction, the other one side doing oxidation, the other side doing reduction, and then there is electron transfer between the two parts. We call each of these parts a half cell. So we have two half cells, each containing all the species inside the half equations, and we connect them through a wire, which allows the electron to be transferred through an external circuit. And we also learned how to annotate these as anodes and cathodes, or negative and positive sides. Okay, so very quickly skipping to the back, so to the end, we discussed some systems with batteries. For example, fruit batteries, we saw how that works. Where the more reactive metals will oxidize and the less reactive metal is the electrode where hydrogen ions in the lemon is reduced to hydrogen gas. And we could calculate the amount of electricity, the voltage that can be generated by knowing which of the metal is the more reactive one. And we also discussed about some commercial batteries, including the zinc carbon battery. One of them is the cheaper, the acidic zinc battery that involves manganese dioxide in ammonium chloride. And that will be reduced in the reaction manganese 4 to manganese 3 oxide. And also we have zinc coating in the outside of the battery that will be oxidized into zinc ions. Okay, so those are the redox reactions, and we calculated that should generate around 1.3 volts of battery of electricity. And then we stopped at the alkaline batteries, which is a very similar system, but instead of having ammonium chloride, we have potassium hydroxide as the electrolytes. So the chemistry is a little bit different, where we have manganese dioxide being reduced to manganese-free oxide, and that produces hydroxide ions. The hydroxide ions, also those in the solution, will react with zinc and oxidize the zinc to zinc oxide instead of zinc 2+ ions. Okay, and we have a semi-permeable membrane. So the ions in solution can travel through the membrane like potassium and hydroxide ions, but the solid reactants cannot travel, like manganese dioxide or manganese-free oxide or zinc oxide and zinc powder. These will stay at the two half cells. Okay, that allows the half cells to be separated. The reductant oxidants don't travel through the membrane because they are solid. Okay, and that gave us 1.43 volts of electricity. So now we're going to look at another type of these cells, and some of us will use these in watches or in calculators. These are the zinc silver oxide batteries, usually called the button batteries. Okay, so these button batteries are more compact, and you may not notice what is inside these batteries. Actually, they contain, again, two different half cells. The top part of the battery is the little knob. Okay, the knob part is actually the negative side of the batteries, so as opposed to the normal batteries where the one with the bit sticking out is the positive. For the button batteries, the bit with the sticking out part is the negative side, and the flat part in the bottom is the positive side. And in the inside, we see that in the top we have a zinc powder together with some potassium hydroxide. And in the bottom, we have silver oxide, okay, together with potassium hydroxide. So we have silver oxide in the bottom of the positive side and the zinc powder in the top side. So again, we get zinc and hydroxide ions. The electrolyte here is potassium hydroxide, which is not written down in this list here, but we have potassium hydroxide solution in the zinc in the silver oxide battery. So we have for the anode the zinc oxidation to zinc oxide, same reaction as the alkaline battery. But for the cathode, we use a more energetic compound, so we can have more energy in a more compact cell. We use silver oxide. So silver oxide will be reduced from silver 1 plus to silver metal. So in this side, we have the reduction, which gains electrons for the silver oxide, and we form silver metal. Again, the side product is hydroxide ions, which can also supply for the reaction at the anode through the separator, the semi-permeable membrane, separating the two solids from the top and bottom. Okay, so if you look at the E values for these two half equations, you will calculate that the overall voltage is around 1.6 volts, a little bit higher than the alkaline batteries. So that's the basic design. So they are a little bit more costly than the normal batteries because they use silver oxide. So they actually contain silver in these batteries. So the cost will be a little bit higher. And in the past, when they make this, sometimes they would try to make it more efficient by adding a small amount of mercury to the cell that will amalgate with the zinc powder and the silver that is formed. Okay, so nowadays they don't usually put mercury in them, so sometimes they will be written down as mercury free. Okay, but in the past there was a problem with the disposal of these batteries, because when you throw them away, they go to the landfill, and then the steel case can slowly corrode away, releasing the contents, and if there's mercury or other heavy metals, they can pollute the environment. Even if they are burned in an incinerator, the mercury can escape as a vapor and going out and breathing. We can breathe them into our body. Okay, so that's the silver oxide battery. Again, if you want to understand the chemistry, you need to be able to write down the correct equations, the half equations. And to find the equations, you can always refer to the data book. All these reactions are in the data book. Okay, so the next part I think is actually moving on to talk about rechargeable batteries. Okay, so as we know, we have discussed 3 of these batteries: the zinc carbon, the alkaline battery, silver oxide batteries. These are single-use batteries, so we use them when they are spent. We would throw them away. Okay, usually the best thing to do is to throw it into a special chemical collector, battery waste collection, so we don't release the heavy metals to the environment. But the more environmentally friendly way is to use rechargeable batteries, okay, which you can charge it and use it several times over and over. So we have to understand how the chemistry works for those. Okay, so basically there are 2 cycles when you're using a rechargeable battery. There's the cycle of the discharge, which is when the battery is being spent in your equipment, okay, whatever it is. So this is the redox reaction that goes in the spontaneous direction, meaning that it is the same as the battery reactions. So we have 2 half cells. One of them is more one willing to be reduced, the other one is more willing to be oxidized according to the energies. Okay, so we can look at the D values, we can decide which one will be reduced and oxidized spontaneously. So those reactions will take place, which will give out energy. The energy will be given out as the electromotive force, or the energy of the moving electrons. Remember my analogy last time, the electron starts off very energetic, and then at the end arriving very has lost the energy when it arrives at the cathode. Okay, so this is the discharge reaction. And then we have another cycle, which is the charge reaction. The charge cycle is where we actually undergo the opposite of the redox reaction. So we have to, the reaction has to go in the non-spontaneous direction. You have to supply energy to push the substances back to the original position. So we can have a little equation to express these systems. For example, when we are undergoing discharge, A star is a higher energy species. Okay, so and compared to A, okay, the one with the star is the higher energy species. So the higher energy A star would go down into A plus E minus. This is losing energy, and also in this case, the B will gain the electron and become another type, the B star, the more reduced form. So there is energy lost in this case. Okay, so but when we are trying to charge the battery, then we have to go in the reverse direction. A has to gain electron again, be reduced back to A star. B star has to go back into B plus E minus. So basically, we have to connect this to the the charger. Okay, so I think it's better to understand it through one of these diagrams. So it's all about energy. When we are using a battery or when we are charging a battery, we are trying to use energy from the battery. So we have a system where we have something being reduced and something being oxidized. Okay, let's say the star is the one that is more oxidized. The one without star is the one that is more reduced. So you can see that from going from the A oxidized form of A and the reduced form of B to the reduced form of A and oxidized form of B, we have an energy difference. Okay, this is the energy difference which gives us a battery. Okay, that's why we have redox reaction when we connect them together into two half cells. So when we are discharging using the energy of the battery, then we have to go from the higher energy set to the lower energy set. Okay, so we have to go from oxidized A to reduced A and reduced B to oxidized B. Okay, so this is the discharging mode. And then for the charging mode, we have to go in the opposite direction. So we have to bring this back up to the high energy level. In this case, we have to supply energy to do that. Okay, so we can write this down maybe in our notes. So basically, we have a system. The discharge is the spontaneous redox reaction. So we go from high energy to low energy. So in the spontaneous one, we will have a release of energy. And this is as electromotive force. Okay, so the moving kinetic energy of the electrons, you can think of it as that way. Okay. The other part is the charging mode, and in this case, we have to increase the energy of the chemicals, increase the chemical potential energy. So this requires energy input. Okay, and this is the non-spontaneous direction. So a charger, by connecting this to another supply of electricity, we can drive this system back to the higher energy level. Okay, so looking at this graph, the question I ask you is which of these reductions would have the more positive E value? Remember, more positive goes forward naturally. Okay, so if we think of these two reduction reactions according to this one, which of them would be more positive? Which one would go forward spontaneously? Okay, so we can answer this question very easily because we can see that the spontaneous direction is to go from the high energy to the low energy. Okay, so we can see that we are going from A star to A and B to B star. Okay, so it means that we have to go in the reverse direction if we are in the spontaneous one for A star back to A, and B goes directly to B star. Okay, so the spontaneous going forward, meaning that B plus E minus would be more positive, and A to A star must be more negative. Okay, so this one is has a more positive E value, so it goes forward in a spontaneous direction. So this one goes backwards. Okay, so hopefully you understand the logic behind a rechargeable battery. Okay, basically now we are adding a cycle of charge that is possible for the rechargeable batteries. In the previous ones, we can only do the discharge for the one-time single-use batteries. But the charge part is too difficult to occur, so it is not possible to connect it to a charger and then push it back to the original form. But we have designed some system, some chemical system, where it is possible to go both ways. Okay, so we are going to see the examples. Okay, so first of all, one of the examples is the nickel metal hydride batteries. These are the most common type of rechargeable batteries that you will buy in the market today. Okay, so if you go out to the shop and buy a rechargeable battery, it's most likely that you're going to pick up one of these NiMH batteries. So let's look at the reaction involved and the setup of the battery. So if you actually open up the battery, you will find that it is a coil of different layers. So it's basically a layer of, you can see it's 1, 2, 3, 4, 5 layers. Okay, let's look at what those layers are. Okay, there's the outer layer, the jacket, so we can ignore that one. There's the steel case on the outside. And then, so the first and the second one are the outer layer. Jacket is the plastic coating, the labels, okay? The silver one is the steel case, okay, that's the outside. Then the green one is now our negative electrode, the metal hydride, okay? So this green layer is the first one, okay? It's going to be our negative electrode. And then we have the yellow one as our separator, so it separates the two half cells. And then in the inside we have a positive electrode, which is a nickel oxide hydroxide. So this is nickel free oxide hydroxide, nickel 3+. And then we have an inner layer of separator. Okay, so then this package, basically the negative electrode, the separator, and the positive electrode, they are rolled up into a battery as a cylinder. Okay, the save space, basically you blow it up, and then they can react through the layer, the separator there. There's 2 layers of separators, so you can roll it up into like 3 of these layers coiled up into a cell. So you can see what is happening. We have basically here a metal hydride. Now, metal hydride is a little interesting chemical. What we have here is metal connected to the H- ion. So usually hydrogen, the hydrogen ion is usually 1+. So we know that we have H+ ions. Okay, that's 1+ hydrogen ions. But here we have a different oxidation number. This is H-. Okay, and H- is known as hydrides. So hydrogen is now the anion, the negative ion of the compound. And then the metal here forming the positive ion is not a single metal, but is made up of a mixture of metals, usually an alloy, with a formula of XY5. So basically you have 2 different metals or even more, and then they have to be in the ratio of 1 to 5. So it's an alloy. It's not really a compound here, but an alloy, mixture of metals. And then we have the XY5 is basically a lanthanide. The one with a lower ratio is a lanthanide. The elements in the bottom part of the periodic table. And then Y is transition metal. So one of the transition metals could be iron or cobalt or nickel. Okay, so we can see in the notes there are a little bit more details. So usually the metals used are lanthanide, lanthanum, cerium, praseodymium, neodymium, or nickel, cobalt, and manganese for the transition metal. But the exact ratio is a company secret. So each company will change this hydride according to their research. Okay, and so therefore there are some differences between the different brands of the nickel metal hydride batteries. I don't know which one is best, so you have to test them and see which one is best for you. But there will be a little bit of a difference in the formulation. But the chemistry is the same. So basically the metal holds on to the H-, and the H- is what is being oxidized. So from H- we have OH- ion, hydroxide ions as electrolytes, and that reacts with the H- to form water. And you can see by forming water, then we have 2 minuses, which has to go out as 2 electrons being lost. So you lose 2 electrons in this process of H- reacting with hydroxide. Okay, and you reduce the hydride to form water. Okay, so you go from -1 for the hydride to +1 in the water. That's why you have lost 2 electrons. So the hydrogen changed its oxidation number from -1 to +1. And then the nickel oxide hydroxide, this compound, if you work out the oxidation number, nickel here is +3. Okay, for the nickel. And after the reaction, it gains an electron and it becomes +2. It becomes nickel 2 hydroxide. Okay. So this is the reaction that takes place. It accepts electron combined with water to form nickel hydroxide and release hydroxide ions. Of course, there's a supply of hydroxide ions and it's used up by the hydride, so it can move across the membrane, the separator, so we have a constant supply of electrolytes. So this one goes from -1 to +1. Okay, so this is our oxidation, this is our reduction. Okay, so this is the spontaneous direction in discharge. Okay, the hydride is oxidized, the nickel is reduced. The common feature for these rechargeable batteries is that we find that we will go from a higher oxidation state of a transition metal to a lower oxidation state transition metal. Okay, so usually here we find nickel is going from +3 to +2. And we'll also see in the other cases where we have a transition metal changing from a higher oxidation state to a lower oxidation state. So this redox reaction generates around 1.1 to 1.4 volts of electricity. And if you want to, once it is spent, then you will have no more hydride, you will have no more nickel 3+, but you're going to end up with water hydroxide and nickel 2 hydroxide. These substances will remain after the battery is spent. Okay, so it's used for the first time, you have used up the energy inside, so you will have this situation: water, nickel 2+, hydroxide and hydroxide ions. So if you want to reverse it and change it back to metal hydride and want to change it back to nickel 3+, then you have to put it to the charger. And once you do that, we can connect this reaction, H2O, to push electron into the water. Okay, so that of course the water is still connected, attracted by the metal alloy here. So the water will be reduced back to hydride by external supply of electricity. And also the nickel 2+ can be oxidized back to nickel 3+ and losing electron into the external circuit. Okay, so we can do the charge cycle. So this is for charging. So we need to supply energy to drive them back to this stage. So these are the higher energy states, basically. And by putting electricity in, we can reduce the H and oxidize the Ni. Okay. And you see we have all these things that is going backwards. Okay, so everything is there inside the battery. Then we can push it backwards. So you see, usually charging requires 1.4 to 1.6 volts, so slightly higher than the discharge energy. So because we're pushing it in the non-spontaneous direction, so we have to give it a little bit more energy to push in that way. So usually we can do this around 500 times before the chemicals are too disintegrated, so we cannot repeat the reaction. So usually you can use these for many times, and that will be more environmentally friendly. So another type of battery I wanted to talk to you about is the lithium batteries. Okay, so lithium batteries, of course, is very useful nowadays. It's found in many things everywhere. Okay, from your mobile phones to watches to cameras to laptops. Everything has lithium batteries inside. And there are two types of lithium batteries, and we have to be careful to distinguish the two types of lithium batteries. There's a real lithium battery containing lithium metal. Those are the non-rechargeable ones, and you can find those also in supermarkets. They are usually the more expensive type of batteries. So you know, when you buy these batteries, there are the normal types, and there are some that are especially expensive, maybe adding to the bill maybe $30 to $40 on top of the original, the cheaper type. And those are usually the longer lasting or gives a higher voltage. And they are good for cameras and things like that for a longer time. And the reason is because they use lithium metal, which is the most reactive metal in terms of the electrochemical series. Okay, so we can look at the system inside and work out what is happening. So this is a button battery containing lithium metal. This is non-rechargeable type. So going back to the non-rechargeable battery, so we have a separator, and then we have a top and a bottom. The top part is filled with lithium metal. Okay, so we actually have a piece of lithium metal inside this part, and then in the bottom we have manganese dioxide together with an electrolyte, which is potassium hydroxide. Okay, so in the bottom we have potassium hydroxide and MnO2. In the top we have lithium metal. What would be the reaction? Let's try and do this by yourself. So in the next page, there's an exercise. There's a space there. So what you need to do is to go to the data book or the list, the electrochemical series, find the correct reactions and write it down. Write down the correct half cell reactions to determine what's happening. Okay, so I can give you the table here. So I should have all the equations on this table. So you need to identify the correct half equations in the correct direction. So think about whether it's undergoing oxidation or reduction, which one is oxidized, which one is reduced, and then try and work out the voltage of the cell. Okay, so let's go through the answers. Now, have you identified the equations you need? So you see that from the battery here, we can identify the materials used in the cathode and anode. We have here lithium, so lithium metal is involved, and we have manganese dioxide, and I told you the electrolyte is KOH. Okay, so we have potassium hydroxide. Okay, so we have to have an equation for lithium metal, and that of course has been oxidized back to lithium plus. Okay, so we have to oxidize lithium metal, and oxidation takes place at the anode. So lithium has to go to lithium ion plus electron. And the E value for this reaction is the reverse of the E value in the table. So in the table we have minus 3.04, and over here we will have positive 3.04 volts. Okay. And for the cathode reaction, we have manganese dioxide, we have OH minus. So we have two equations involving manganese dioxide. We have here the MnO2 forming OH minus. Okay. We have also this MnO2 plus NH4 plus, okay, forming ammonia. Now, of course, we don't have any ammonium ions. We don't have acids, but we have hydroxide. So we have to use the alkaline condition equation, which is this one. Okay, so we can copy this down. So this is our cathode reaction. Of course, remember this is the reduction. So we have to gain electron. E value is from the table plus 0.15 volts. So to deduce the overall reaction, we have to make sure the number of electrons is balanced. So we can cancel out the electrons term. So to do that, we have to multiply the top equation by 2. Okay, and then we can add the two equations together to give us the overall equation. And the electrons term cancel out. Okay, so the overall reaction is found by balancing number of electrons in both equations and then adding up together. The left side, what's on the left side add up together, what's on the right side add up together. And anything that is the same on both sides get cancelled out. The voltage of the cell is the addition of the two numbers, remember that? So we can find out the voltage of the cell by doing 3.04 plus 0.15 volts. So get 3.19 volts. Okay, so we should get around 3.2 volts, and indeed the battery containing lithium is a 3-volt battery. Okay, so this is a 3 volts battery. Let me ask you an IQ question, or maybe a not common knowledge question. So you know you can buy 9-volt batteries. Okay, have you seen those 9-volt batteries? 9-volt batteries are also alkaline batteries, just like these ones. Okay, how do you get 9 volts out of these batteries? Because if you add up the numbers, even the most electropositive and most electronegative ones add up together will only give you around 5.8 volts. So how do you get 9 volts out of a battery? Any idea? Anyone knows how you get 9 volts from a battery? Okay, so the answer is by connecting cells in series. Okay, so indeed you can only get 1.5 volts because there's the limit of the batteries, but you can connect a few of the cells in series, so the voltage will add up. So if you take 6 of these batteries of 1.5 volts and connect them together in series, then together you will get 9 volts out of that. Okay, so that's how you get 9-volt batteries. Okay, basically there are 6 cells inside. Each of these is the size of AAAA, 4 A's. Okay, this is the 4A size batteries fitted into this rectangular box. Okay, so that's how it works. So now you know. So just by using the chemicals reaction by itself as a single cell, 3 volt is already a very high voltage to be generated. Okay, you needed already the most reactive metal, lithium, that gives you the highest E value. It's even a higher E value than potassium or sodium. Okay, because it's more willing to be oxidized. Okay, so now you should be able to do these kind of questions by yourself, right? You get a chance to practice later in end of chapter exercise and in the quiz, second quiz. That will come up at the end of chapter 6, okay? All right, then let's talk about the more important type of lithium battery. Now we are talking about lithium-ion batteries, okay? So you have to make distinction between lithium batteries and lithium-ion batteries. And most of the time when we are talking about lithium batteries, we are actually talking about lithium-ion batteries. These are the batteries that are found in our phones, in our computer laptops, and also other rechargeable lithium batteries, okay? So they use lithium-ion. There is no real lithium metal inside these batteries. You cut it open, you won't find a piece of lithium metal. So let's see how this works. So basically, the lithium-ion batteries works by migration of lithium ions. Okay, so there's lithium ions, lots of lithium ions inside these batteries, and they swim between the positive and negative electrodes. Okay, so there's swimming happening. The lithium ion is likely to swimmers, and it swims across either from positive to negative or from negative to positive, depending on whether it's charge or discharge. Okay, so it's basically a battery to allow the swimming of lithium ions. Then of course we have to understand why would lithium ions move around and why does this generate electron movement. So the materials used for the positive and negative electrodes are important. The negative electrode is made of graphite. Okay, graphite is a form of carbon. It's an allotrope of carbon. And the positive electrode is made of this compound called lithium cobalt oxide. Okay, so with the formula LiCoO2. So let's look at graphite first. Okay, graphite is one of those structure that we call giant covalent structure. Okay, so this is what we haven't taught you. So giant covalent structure is another type of materials in the covalent bonding. So I've taught you about covalent bond in the second chapter, and we looked at some covalent bond molecules like oxygen or nitrogen or water. So these are molecules with covalent bonds inside. Okay, and they are small molecules, they're usually a gas or liquid with weak intermolecular forces attracting each other. But there is also a type of materials which is also made up of covalent bonds, but instead of having individual small units, we have lots and lots of atoms, like billions and billions of atoms, all connected together into a single structure by strong covalent bonds. Okay, so not individual units by weak intermolecular forces, but lots and lots of atoms all bonded together by strong covalent bonds. And those are known as giant covalent structures. And we have some examples here. Diamond and graphite are both giant covalent structures. So you can see lots and lots of carbon atoms, only a few are shown, but in fact the structure is extensive, containing billions of atoms, all joined together through strong covalent bonds. In graphite, you have a slightly different structure where we have different planes. These planes are very large, okay? You can imagine millions or billions of atoms in a plane, but the planes, in between the planes of these huge amount of atoms, they are only attracted by some weak intermolecular forces between the layers. Okay, so we have some layers with lots of atoms, difficult to break all these bonds, but you can slide between the layers easily. They can move apart. So the layers are attracted only weakly to each other. So that's why you can use graphite as a pencil, because when you're writing with pencil, what you're doing is rubbing a layer of graphite onto the paper by breaking this weak intermolecular force as you use your force from your hand to rub the pencil lead onto the paper. Okay, so this is structure of graphite. This is one for diamond. So diamond is very hard and strong because all these bonds are very rigid, very strong. You cannot break it easily. So diamond is the hardest material we find. But what we have in our batteries is graphite. And this structure, the layered structure with the weak forces between the layers is very important because there is a hole, there's a gap between the layers. And this gap here allows lithium ions okay, to go inside. So a little reminder, giant covalent structures where we have lots of atoms linked together by strong covalent bonds, okay, rather than just small units of molecules linked together by attracted by weak intermolecular force, and they tend to have very high melting points, such as graphite and diamond, both are very high melting solids, over 3,000 degrees. Okay, so we can have lithium ions going into the layers between these graphite layers. Okay, so lithium ions can swim inside and form a new compound. We call this a lithium graphite compound. There are different ratios of lithium to carbon, but there's a common one which is LiC6. So for each 6 carbons, like each ring of the carbon, we get 1 lithium ion, okay, on average in this ratio. Okay, so we will use this as our typical compound, but they can also occur in other ratios as well. Okay, so lithium ions can swim into the graphites and form a compound, lithium carbon compound, lithium graphite. Okay, so the other material for the positive electrode is made of lithium cobalt oxide, and this is more like a ceramic material, okay, like the porcelain that you have for your bowls or other ceramic materials. And the structure of this is an ionic compound, it's an oxide, so there's O2 minus ions, there's lithium ions Li plus, and there's also a cobalt ion. The cobalt can be 3 plus or 4 plus. And you can see the structure arranges itself in a giant ionic lattice, a bit like the sodium chloride or the cesium chloride structures we have seen. But of course, it's more complex because we have 3 types of ions. So this is called a perovskite structure, and it's a little bit more complex. I'm not going to go into the detail of the lattice structure. But you can see where the oxygen atoms are, and it's surrounding lithium ions as well as the cobalt ions. So cobalt positive ions, lithium positive ions are surrounded by the negatively charged oxygen ions. Of course, the oxygen is also surrounded by positively charged lithium and cobalt ions. Okay, so the basic structure like that. Of course, here the lithium ions are also quite small, and it's fitting not very tightly in this hole. So it's also possible for the lithium ions to swim out of the structure. So when the lithium ions swim out of the structure, what we're left behind, if we have LiCOO2 to start with, we are left with COO2 without the Li+. Okay, so this is a reaction where we can express this as reduction of the lithium cobalt oxide. Okay, so you can see here from lithium cobalt oxide, the lithium ion can swim out of one of these sites, and in that site we will convert the cobalt into cobalt 4+ in order to maintain this as neutral. And the lithium, an electron has to leave the system together with the lithium ion. So this is a reduction of the lithium cobalt oxide. Cobalt goes from +3 in this substance. You can work this out. Oxygen is -2 times 2, so it's -4. Lithium is +1, it's a group 1, so this is +3. And going to COO2 it becomes +4. Okay, so +3 to +4, this is an oxidation of the cobalt ion. Okay, so this is what happens. Well, you can lose lithium ions from the structure, but how much you can lose until the structure is no longer able to stand it? There's a maximum loss of 50% roughly. So you can imagine that lithium ions are also there as a structural thing. You can like little pillars to hold the structure in place. If half of these, more than half of these have gone, then you have lost too much support and the structure will start to collapse. Okay, and when it collapses, then it becomes irreversible. Once the structure has collapsed, you cannot have any spaces for lithium ions to swim back into. Okay, no more holes left behind, so you cannot charge the battery again. Okay, so there is a maximum loss of 50% of the lithium ions. Greater than 50%, we start to collapse the structure and have some irreversible reactions. Now the lithium ions are swimming, and they're swimming in a bath, which is an electrolyte material. And the usual compound for making the electrolyte is a salt of lithium, which is lithium hexafluorophosphate. The reason we chose this salt is because this is soluble in an organic solvent. So this is not, we don't use water inside because water would hinder the lithium ions from moving, because water tends to attract very strongly the lithium ions and also destroy some of these compounds like the lithium graphite. So we use an organic solvent, dimethyl carbonate is a common choice. So you can see it is carbon carbonate. You can see the middle part is our carbonate CO3 2-, but instead of CO3 2-, we have 2 methyl groups, CH3 groups attached to the oxygens. So it's called dimethyl carbonate. It's a liquid, okay, flammable liquid, organic solvent, and lithium hexafluorophosphate can dissolve in its organic solvent. So we have a lot of lithium ions in this electrolyte trying to in the reservoir. And what we have to do for the reaction to happen is for the higher energy material to the lower energy material. So what happens is when we are undergoing discharge, like when you're using your batteries now in your pocket, the lithium ions are swimming out of the graphite. Okay, it starts off as the lithium graphite compound, and it's swimming across to go back into the holes in the lithium cobalt oxide ceramic, okay, in this lattice structure. So when you have charged your phone and your batteries, you should have all the lithium ions filling up in the graphite structure, and then there are lots of holes inside this ceramic structure of the LiCoO2. And when you're using the phone, lithium keeps swimming across from this side to that side, and there's redox reaction taking place. So we can write down the equations. So when lithium ions swim across and out of the lithium graphite compound, then we would have free lithium ions returning the carbon to the graphite, and we also bring it with the lithium ion and electron. So this is a loss of electrons, the oxidation happening here. So we can work out what is being oxidized. The substance being oxidized here is the carbon, because in lithium graphite, in this compound, the carbon here is in oxidation state of because lithium is +1, so what's the oxidation state of the C here in this LiC6? Okay, so they have to add up to 0. So what is this value here? It has to be -16, right? So the oxidation number for carbon here is -16. But when it goes back to the element, this is graphite element, so this is 0. Okay, oxidation state 0. So we have an oxidation of the carbon. Okay. So you can see oxidation states can indeed be fractional numbers. Okay. So when lithium ion swims out of the lithium graphite, then it goes over to the empty sites in the lithium cobalt oxide, and so this is an empty site. So this is cobalt +4, and it goes back to cobalt +3, and it gains an electron. So this is the reduction. So in the charging process, what you can see is the lithium ions will be swimming across. Oh, sorry, I draw the wrong side. This is the graphite, right? This is the lithium cobalt oxide. So the lithium should be swimming from the graphite over to the lithium cobalt oxide. So it's going out there. Now, of course, we have a lot of electrolytes in between the two electrodes. This is a solution of lithium phosphate in the carbonate, in the dimethyl carbonate. So there are lots of Li plus already. So it means that the lithium ions don't have to swim all the way from the graphite over to fill a site. What is going to happen is just that one of the lithium will go out of the graphite, and another one from the electrolyte can fill in the hole. Okay, so it's much faster. If you have to wait for one to travel over, then it is limited by the rate of diffusion. Okay, so one goes out here, the other one can go into a hole there. So it's very fast reaction. And that's why we need a lot of lithium ions in the electrolyte there to make sure this transfer of lithium ions is fast. And then there's redox reaction taking place. And when this takes place, the E values will give us a value of around 3.7 volts, okay, roughly. It depends on the ceramic materials. So in the more advanced lithium batteries, what they're trying to improve is the ceramic materials. So of course, when we are putting this to the charge at night, what happens is the reverse. So when we have used up our batteries and our phone tells us you have to charge it, that's when the lithium ions are very few in the graphite, and most of them have gone back into the lithium cobalt oxide. So when we charge it, we have to push the ions back over to the graphite side. Okay, so it departs the lithium cobalt oxide, okay, forming cobalt oxide again, and it swims across over to the graphite, filling up the graphite holes, forming lithium graphite compound, LiC6. Okay, so that's the reverse of the reaction. Now, of course, when you're using your lithium-ion batteries, there are two things that you might have heard of. The two advices, if you want to have a battery with a longer lifetime, protect or preserve the lifetime of your battery is not to overcharge your batteries, right? You have heard the stories. People will tell you don't overcharge it, don't put it in the charger for too long, okay? And also not to drain the battery too much, to over drain the batteries. Both of these advices have chemical basis, okay? It's not just some myth. Okay, you can explain the reasons. That overcharging the batteries will, what are we talking about? Overcharging means that we are going in the reverse direction. So lithium ions is swimming out of the lattice and going back to the graphite. Remember that when you swim out, when the lithium ions leave the lattice, we're left with a gap, with a hole. Okay, so we can only have up to 50% of the lithium ions removed, and otherwise it would collapse and form some irreversible reaction. This is what happens if you have too much lithium ions going away. The structure will collapse if you overcharge. Okay, trying to push too much of the lithium ions out of the lithium cobalt oxide structure, you will permanently form some cobalt oxide, cobalt 4 oxide. Okay, some of the parts will collapse, and then you have no more space for the lithium ions to go back. This is actually a major structural defect in a battery that has been used for a long time. So even though if you take care not overcharging it, there will be some form of collapsing of the lithium cobalt oxide structure over time. So as you know, when you use your phone batteries, after the first time you use it, it's very good and you're happy with the phone battery, it can last you 2 days. But after 1 year, okay, the battery starts to don't work so well, and you have to charge it almost every day, and you have to bring some kind of external charger with you to go outside to last for a day. Okay, and that's when the lithium cobalt oxide is actually a lot of the places has collapsed. So you have a weakened amount of storage for the electricity. Over discharge, meaning that you're draining your battery too much. Beyond 0%, you're still trying to use the last bit of battery, keep switching back on your phone, okay, getting the last message out. That can also destroy the battery, because when we're discharging, we're pushing the ions out of the graphite. The graphite side is okay, but the lithium cobalt oxide is trying to accept too much lithium ions. So you're trying to over-reduce the cobalt, okay, push too much ions, lithium ions into the lithium cobalt oxide structure, and you can force it to do that. And what is going to happen is that it will form cobalt 2 oxide instead of cobalt 3 oxide, which is LiCoO2. You will change the LiCoO2 into COO, which is cobalt 2 oxide, and the lithium will also become lithium oxide. And of course, these forms of oxide cannot go back to lithium cobalt oxide. It's irreversible. So also you can permanently damage this ceramic structure. Okay. So these are the reasons, the chemical reasons for not to overcharge and over discharge your batteries. Okay. So you can pay a bit of attention here. So this is over reduction of the cobalt from +3 to now +2. Okay. And this is irreversible. Okay, so now you know, and of course the new batteries are always trying to produce a new type of ceramic which is more resistant to this kind of overcharge and over discharge destruction of the structure. And the new batteries now don't use lithium cobalt oxide, they use another form with different metals or different ratios of these things. If you look it up, you can find a lot of information on the internet about these. Okay, so I think I finished the chapter, and I taught you what happens when you have lithium-ion batteries, lithium batteries, and other rechargeable batteries. So this chapter may be a little bit more complex in terms of the chemistry knowledge, because we have covered a lot of electrochemistry, and I will do a little bit of summary, just like a revision notes for you to help you revise for this part. So basically, you need to know the definition of these terms: reduction and oxidation. Remember oil rig. Okay, oxidation is a loss of electrons. Reduction is the gain of electrons. Okay, and also remember what is the meaning of cathode and anode. These are the places where reduction and oxidation occurs. Cathode has a C, reduction has a C. Anode has an A, oxidation has an A. Okay, so that you can remember that. So we have talked about 3 types of electrochemical reactions: electrolysis, okay, electrochemical cells, which is batteries, and also rechargeable batteries. You can see the anode and cathode changes sign, okay, as you do these different types of things. So make sure you're not just associating anode and cathode to positive or negative, because they change. Here's a list of things that you should understand. In electrolysis, you should understand how to predict the products from electrolyzing molten ionic compounds or the aqueous solution of ionic compounds using the E values. And you should also be able to predict whether you can do electroplating or metal refining according to the E values, and also suggest what to put in the bath, okay, what is the solution, what to use as the cathode and anode, and also how to anodize metals like aluminium. For electrochemical cells, you should be able to form an electrochemical cell from two separate half cells through a salt bridge and be able to calculate the voltage from the cell. And also to understand what happens when you put two metals inside a solution like a fruit battery, like in lemon, and also to have some knowledge of what happens in commercial dry cells, like zinc carbon, alkaline, silver oxide, and lithium batteries. These are the non-rechargeable ones. And these are all electrochemical cells. Make sure you know which equation in the table is associated with these different types of batteries, so you can use them correctly. And for rechargeable cells, we looked at the examples of lithium metal hydride and lithium-ion batteries, and have some basic knowledge of the electrodes and the chemistry that takes place inside. Okay. So in the exam, the most likely thing that we will really examine you on is how to use the E-values to make predictions. Okay, and there are two predictions you should be able to make. The first prediction is to predict the outcome of electrolysis, especially in solution. So you need to compare the E-values against the E-value of the reduction and oxidation of water. And also to predict the voltage of electrochemical cells. So when you have two half equations connected together, which one will be oxidized, which one is reduced, and what is the voltage obtained. Okay, so those are the things you should be able to do. Okay, so this is a checklist for you, so you can check yourself and make sure you tick all the boxes. All right, so we still have 20 minutes. What I'm going to do now is to, before we move on to chapter 6, I will play to you a short video as a little break. Okay, so this is a series of video. There are 3 of these episodes, and they are made by one of the previous professor for this course, Professor Shu-Kui Kwan. And this is about some daily life chemical phenomenon in a story series. Okay, so I will play you the first episode, and then we'll watch the next ones later. Let me find the video here. This is in Cantonese, I think. So with English subtitles, I think.
，sorry，我冇心㗎。你可唔可以倒機啊？
哦，唔緊要啦，部機都平時好壞㗎啦，都諗住換。
唔係啊，不如你拎去整啦，我賠翻錢俾你。
唔使啦，
唔係啊，冇啦。
差唔多上堂喎，你係咪嗰邊啊？
唔係啊，你拎去整啦，我賠翻錢俾你，因為我唔好意思。唔
使嘅，我覺得。
唔係，你有冇紙啊？俾我。
我揾埋支筆啫。
Jean 唔使用筆就可以喺張收據度寫低佢嘅電話號碼呢？因為嗰張並唔係一張普通嘅紙，而係一張熱感紙，亦稱為 thermal paper。Thermal paper 係應用咗酸鹼化學反應嘅原理。Thermal paper 上邊有兩種化學塗層，上面嗰層係一種對酸鹼度敏感嘅染料，而下面嗰層係對熱力敏感嘅酸性材料。當下面嗰層嘅酸性材料喺受熱嘅時候，就會溶化釋放出質子，將周圍嘅環境變成酸性。酸性嘅環境會進一步將面層嘅化學染料從無色變成黑色。所以只要產生到熱能，就可以喺 thermal paper 上邊寫字㗎啦。頭先阿 Jean 用手指刮嗰張收據嗰陣時，就因為摩擦而產生咗熱能，咁樣佢就可以喺 thermal paper 上邊寫低佢嘅電話號碼。從60年代到而家 ，thermal paper 已經被廣泛應用。我哋平時喺 canteen 超市裏邊用嚟打印收據嘅機器，都係用緊同一樣嘅原理。呢樣都係我哋日常生活中接觸到嘅一個酸鹼化學反應嘅例子。
喂，唔使唔該，拜拜。
點啊，女女啊，唔使啊，
垃圾電話啫。
垃圾電話。不你冇安裝小紅來電 Apps 咩 ？block 到好多垃圾電話喎。
冇啊，唔得閒搞啊。
等我幫你裝翻個啦。
搞嗰啲嘢啦。
樣子喺度，阿 Ray 小秘密。
俾翻嚟啊！
唔俾喎。
俾翻我啊！
喺度唔俾。
阿 Jean 嘅電話號碼點解會消失呢？秘密亦都係因為酸鹼化學反應。酒精係一種極性嘅溶液，佢可以溶解 thermal paper 上邊酸性塗層，從此產生大量嘅質子，令到 thermal paper 嘅字變咗一笪黑色，咁就冇辦法睇到之前上面寫嘅嘢㗎喇。
喂，唔該，我想揾阿 Jean 啊。你係 Jean？我係 Ray 咧，嗰日小巴站嗰個咧。
Okay, so do you know what happens with Jean and Ray? So we'll watch the next episode next time. So make sure you come to the lecture. Right? Okay, so now we're going to make a start on chapter 6, shall we? Okay. Just make a quick start, talk about little things, and then we'll finish. And then, of course, we're coming back later after dinner for our tutorial class here. Okay, starting at 6:45. Yeah, 6:45 p.m. We'll start back here. Okay. So this chapter is about fire and fuels. Okay, interesting topic. Okay, so but it's very important to actually talk about fire and of course what produces fire, and also how can we put out a fire if there is a fire that goes out of our control. So I'm going to tell you a lot about fire in this chapter. Now let's think about fire for a moment. Okay, so sure that you have all used fire before. What do you associate with a fire, and why? What is a fire in fact? Okay, so of course fire is related to high temperatures. Why is it a high temperature? Why is there a high temperature? Well, because a fire is a chemical reaction. There must be oxidation reaction involves between the fuel and oxygen gas in the air. And the reaction is highly exothermic, highly heat releasing. So lots of energy is being released as the fuel reacts with the oxygen. That's why we have a high temperature in the fire, because it's releasing a lot of heat from the chemical reaction. The second thing you might see, you might associate with a fire is the flames has this kind of shape. If you were to draw a fire, you would draw some kind of shapes like this, right? Some kind of variable outline, some kind of tongues of the flames. Why do we get this kind of shape in a fire often? This is actually to do with the things that are burning. Okay, what is actually happening in the burning reaction is actually that the fuel has to vaporize into a gas before it can react with the oxygen. Okay, either you're burning wood or liquid fuel, you have to turn it into gas first. They vaporize, okay, form a gas. And also in the process, you form a lot of hot gaseous products, carbon dioxide or water. There's a lot of products from burning things. And all these gases and the fuel are forming the glowing mass here. So what is the flame is actually a mass of gas or ions that is glowing with giving out light. And these, because they are gases, they will be moving around and don't take a fixed shape. Okay, so they are usually some kind of tongues which are blown around by the hot air, by convection current and so on. So we see this variable outline because they are mostly gases. Okay, the reaction is happening in the gaseous phase. Okay, we are dealing with gaseous reactants, gaseous products. The next is the color and light of a flame, because a flame usually has a color, most commonly orange, and also that the flame emits light. As you know, burning, you can see the fire because there is a lot of light coming out from a flame. Why is there color and light? Well, this is to do with electrons inside the reaction mixture being excited and relaxing. So remember, when you have light coming out in chapter 3, it's to do with electrons going up higher energy levels and then dropping down to lower energy levels. So this up and jumping of electrons in these energy levels is what gives us the colorful flames, the color of the flame and the light of the flame. Okay, so we release light when electrons go from a higher position to lower position. Okay, so you have to understand that these things are happening. That's why we see the flame. Okay, so these are already in the notes here. You can find them here. For example, the color and light comes from relaxation process of the electrons. And then we have also the variable outlines, mostly gaseous products, and also the high temperatures because of the exothermic reactions. Okay, so the reasons are in the notes. Now, what do we use flames for? Okay, fire is very important to human civilization. For example, you use fires for cooking. We eat cooked food rather than raw food. They produce light. Sometimes we use candles. In the past, of course, without electricity, we have to rely on a flame to provide light, so we can see in the dark. Having fire, then you can allow human to do a lot of things like meteorology, production of metals. Remember, to produce the easiest metals like brass or copper or iron, you need to heat up the oxide with the charcoal, with the carbon, to a very high temperature, 1,000 degrees or more, before you produce a metal. So you need a fire to be able to produce metals. Fire is used for defense. For example, if you talk the past in the history, if you are fighting with a lion in the wild, then the most likely thing you would do is to have a burning torch or something that would scare away the wild animals. The animals cannot make a fire themselves, right? So it's very important to human civilization. So we have to understand what happens when something burns. Okay, burning is a chemical reaction. We call this a combustion reaction. Okay, so the word combustion means burning, and it signifies the oxidation of a fuel using oxygen gas as our oxidizing agent. So we use oxygen gas as the oxidizing agent there. And if you use oxygen gas as the oxidizing agent, then what does it become? It becomes reduced. It becomes oxides, okay, in O2 minus form. So oxygen gas usually forms oxides. So the combustion products are usually oxides of the fuels. If your fuel contains carbon and hydrogen, which is the most common elements contained in the fuel, most of our fuels that we use today are made of contains carbon and hydrogen atoms. So if you burn them completely, you will form carbon dioxide and water. We have already seen this in our chapter 3 when we talked about global warming and where carbon dioxide comes from. It comes from burning of fuels. But if you have other elements in the fuel, if you had sulfur, nitrogen, or chlorine, they will form different products. Chlorine sometimes forms hydrogen chloride if you have a source of hydrogen. Okay, because chlorine is not easy to oxidize to oxide. Okay, you can form nitrogen oxides, you can form sulfur dioxide, for example. If you think about burning something, let's say burning paper. Paper, for example, is made of cellulose. It's a type of polymer of glucose. Okay, so this is the structure of cellulose. These individual rings are rings of glucose, which is a sugar, simple sugar with 6 carbons, 1, 2, 3, 4, 5, 6. Okay, glucose is a formula of C6H12O7, O6. Okay, so it's 6 carbon, 6 water molecules. We can abbreviate the structure of glucose to C6H1005. So we have to lose the water when we put them together into a chain, and there are n number of units of this C6H1005. So that's 1 unit of the glucose inside the cellulose chain. When we burn them, we take oxygen and we will produce carbon dioxide and water. So when we're burning paper, then we change it into carbon dioxide and water. So we can balance the equation. You see we have 6 carbons, we will form 6 carbon dioxide. We have 10 hydrogens, that will give us 5 of the waters, because each water has 2 hydrogen. So we can come back then to work out how much oxygen we need, okay, by counting up the oxygens in the products. Okay, and that's the amount of oxygen we need. So that's an example of the reaction. How do we know we have carbon dioxide and water? Well, we can tell by doing a chemical test. And the test is to pass the gas from a burning reaction into 2 test tubes, one containing a chemical called cobalt chloride, usually on a test paper. And the other one is a test tube of lime water. Now, cobalt chloride is used to test for the presence of water. So this has to be the first one because there's water in lime water. Okay, so you have to pass it first to this test tube. And as the water vapor cools down from the burning, okay, it starts off as water vapor, and it cools down, it will form drops of water. And when the drops of water comes into contact with cobalt chloride paper, the dry cobalt chloride paper has a blue color in the anhydrous form of the cobalt chloride salt. But when water comes in, it forms a hydrated salt. Okay, so it becomes COCl2 with some H2O attached to the structure, and that has a pink color. So it will change from blue to pink. Okay, and that's what we will see. And for sometimes we use this cobalt chloride in our silica gel. So sometimes you find these packages of desiccant in your food, and there will be some dots which are blue colored, like this one and that one, right? Those are the blue color ones. And as the gel expands and water is absorbed, then the cobalt chloride changes from blue to pink, and that tells us the silica gel has to be heated again for reuse. Okay, so those are indicator of the silica gels whether it's absorbed or not, the water. Lime water is used to test for carbon dioxide. Okay, so here is a test for carbon dioxide where lime water turns milky. Okay, turns milky color or white precipitate is formed in the lime water as carbon dioxide reacts with the lime water. We can write down an equation for this one. This is where CaOH2, which is lime water, reacts with carbon dioxide to form calcium carbonate, which is insoluble, and water. So this is white precipitate. And it gives us the milky appearance of the lime water. Okay. So that's the chemical reaction. And so lime water is used as the reagent to test for carbon dioxide, and dry cobalt chloride paper, the blue one, is used to test for the presence of water. So some chemical tests here for you. Remember, we have also taught you other ones like oxygen relights glowing spins. Okay, putting glowing spins in the oxygen gas relights it. Hydrogen burns with a pop sound. We have heard that last time. Okay. Okay, so I think I stop here, and I will come back to the next page next time. So now you can go, if you are going to come back for tutorial, we'll start in 1 hour, so it's around 6:45. So you have around 55 minutes to take a break, have some food, and see you later.